Hey everyone, I'm Max. Let's learn how to tackle this educator problem, a simple graph. That was the question mark at the end, in case you couldn't tell. Essentially, what we're asked to do here is we're given a list of edges just as pairs, and we want to determine if they constitute a simple graph. What is a simple graph? Well, a simple graph doesn't have self-loops or parallel edges. Let's draw that out real quick. So here we can see that we have 1, 2, 1, 3, 1, 4. So we have a node 1, 2, 3, and 4. 1, 2 implies that there's a path going from 1 to 2, an edge going from 1 to 2. You can see it is in fact directed. So we can go from 1 to 2, but not back from 2 to 1. There's also an edge going from 1 to 3, and one going from 1 to 4. This graph is simple because it doesn't have any self-loops. What is a self-loop? Well, a self-loop would just be an edge going from a node to itself. So say 1, 1 here would look like something like that. And 1, 1 would actually be represented as 1, 1. So when we're iterating through those pairs, it should be pretty easy to tell what a self-loop is. It's just the same node in the pair twice. It also doesn't have any parallel edges. A parallel edge would be something like 1, 2 again, right? Again, you should kind of start to get an idea. Here, a parallel edge is just the same pair of two nodes that we've seen before in the edge list. One thing I do want to note is that something like this, a 4, 1, is not the same as having a 1, 4. And that's because this is a directed graph. Here, having an edge from 1 to 4 indicates that maybe you can go from 1 to node 4. Having an edge from 4 to 1 notes that you can go from node 4 to node 1, not the other way around. So again, this is a directed graph, which means the edges only go one way. Having edges in two distinct directions are two different things. And so we don't need to check if if we're given the edge 4, 1, we don't need to check if 4, 1 and 1, 4 is already in the graph. We just need to check if 4, 1 is already in the graph. So that's really all there is to this problem. It's pretty straightforward. We just want to look through all the edges and check if there are any self-loops, which again is just having the same node twice in that pair, or having parallel edges, which is having a duplicate edge from earlier. This exact same pair we had earlier. Now, let's start to write. Let's clear all my drawings. Let's start to write some code while I talk about hashing functions. So here, one thing we want is a way to check for duplicates in our pairs, right? And you might immediately think, okay, I can use a set, right? A set, a pair, int. What this will do is when I insert a pair, I can check if it's already in the set. And if I insert a duplicate, it's only ever going to have one. So it's an easy way to tell if there are duplicates. Now you might also, go a step further and say, well, I don't actually care about the ordering of these pairs in the set. I just care that they exist within the set, whether they exist in the set or not. So I'll make it an unordered set. Now, the issue with the unordered sets are built with hashing, right? You can insert a certain pair, and then if another pair is inserted later that hashes to the same value, they are effectively treated as duplicates. The issue is C++ does not have a hashing function for pairs or even vectors of integers built in. It does have a comparator, which is why set works, right? They can compare pairs between themselves, but it cannot hash pairs. So it won't actually let you use this unordered set. Before I continue, I want to say doing something like this, just hashing pairs, I guess here it wouldn't be hashing because it's an ordered set, but using an ordered set to store pairs is a completely valid way to do this. But what if you wanted to keep that O of 1 amortized complexity that you get with these unordered maps and sets. You're gonna have to do a little bit of extra work. So what you could do, for instance, is make an unordered map that links targets to an unordered set of destinations. So essentially, you could map 3, or better example here, 1 to a set of 2, 3, 4, because 1 has targets 2, 3, 4, has those destinations when 1 is the source. And this way, you're only ever hashing integers, which C++ can do just fine, but you're still, again, using those unordered structures for that O of 1 time complexity. So let's try that. We will have to import these, so unordered map, unordered. And we'll call this targets, because it represents, given a node, what it's currently pointing to with the edges we've given it so far. So then it should be pretty clear at this point that we want to examine all the edges. So we'll just loop over all of the edges. Here, each iteration, each edge is a pair of 2 integers. Probably it's nice to know this, but here I'm just going to use the auto keyword to represent that. Now, first thing we'll do with each edge is check if that edge constitutes a self loop. So like we talked about, a self loop is just when the source of that edge, first node, is equal to the second node, the target of that edge. And if that's the case, then we'll just return false, because we know that if there's one self loop in all the edges in this graph, the graph is not simple. So again, just return false. Next thing we'll do is we'll try and evaluate the targets. So again, we want to check if the edge that we're now evaluating, E, has already been put into this target's map set, however you'd like to do it. So I think it's pretty clear that after every loop, what we can do is we can say targets E dot first dot insert E dot second. And what this will do is this will go right here. It'll check the corresponding set associated with E dot first, that source, and add E dot second as a target of that. So, if we evaluate it here, it would push back 2 to the set corresponding with 1. Here, it would push back 3 to that set corresponding with 1. So now that set has 3, 2, and so on and so forth. But here, before we push, we can actually, or we insert, I guess, in the case of a set, we can actually check if that value is already in that set. If there is, we know there's a parallel edge and we should return false. So how we can do this is we can use, so targets E dot first gives us that set we want. We can use dot count. This will return the count or the number of matches of that E dot second in that set. So we can say, if that's equal to 1, we return false. Now another small tangent here. Here, count will return 0 if we don't have a duplicate, and 1 if we do have a duplicate. And here we're just checking, is it equal to 1, right? Do we have that duplicate being returned? But remember that in C++, a 0 evaluates to false, and a 1 is true. So this condition is actually not necessary at all. If it's false, or if this dot count returns 0, we don't have a duplicate, and we can proceed with the code. And a 0 here will evaluate to a false in the if statement, so it won't run this code. If dot count returns a 1, that means we do have a duplicate, and we want to break the code and return false. A 1 will evaluate to 1 within the bounds of this if statement, or sorry, we'll evaluate to true within the bounds of the if statement, which will return false as we desire. So this code, or this condition, will do exactly what we want it to, even if we don't use a double equal sign. Just a little fun thing to note if you ever want to slim down your programs. So yeah, we've checked for self loops, we've checked for parallel edges. Let's run our code. I can see an issue. Here it's returning 32, which presumably is just undefined behavior. Let's return true at the end if we've checked all edges and nothing is out of the ordinary, just so we can get a more standardized output. Let's see. Looks like all test cases have passed. Awesome. Here's the full code. You can't really expand this window, so you might have to pause and look through it yourself. But yeah, good luck with the implementation. If you have any questions, feel free to reach out to any of the TAs, and best of luck with the rest of the course.